Welcome to another episode of the Concrete Logic Podcast. And today I have Traves Ogilvie with me. He's a founding member of the Synthetic Aggregate Association. So guess what? We're going to talk about synthetic aggregates. Good guess. But before we get started, as I always remind you all, actually, you know what I'm going to do today? If you're watching on YouTube, and there's a lot of you watching on YouTube, why you want to look at my mug while you're listening to this, I don't know, but we'll go ahead and share screen here. As I always say when we do one of these episodes, there's several ways you can help out the show, support the show. And the first thing you can do is share it with a colleague or a coworker in the industry. If you found something unique or you learned something from the episode, please share. The second way you can do is reach out to me, and there's a couple ways here. So if you're looking at the screen, there's a contact button here. You click on that. That's like leaving me an email, and then at the bottom right hand corner here, there's a little microphone. You click on that, and there's a little start recording button there, and that's like leaving me a voicemail. So there's a couple ways to get a hold of me. And what I'm looking for are topic or guest suggestions. So please reach out and let me know what you want to hear on the show. And then the last way is up here. There's in the upper right hand corner of concretelogicpodcast.com. There's a little donate button. You click on that and you can give any amount. And it's through, I believe, we're with PayPal. And you can leave any amount you want. Any amount is appreciated. Just helps us keep this thing going. And that's all I got for you as far as that. We're going to get right into it with Traves. He's going to, like I said, teach us about synthetic aggregates, which I don't believe I think we've had some maybe adjacent episodes to that, but haven't talked about it specifically yet. So Traves, please introduce us to synthetic aggregates.
Awesome. Thanks, Seth. Thanks for having me. Appreciate it. Synthetic aggregates is quite a passion of mine and some of my colleagues. So we started in Q4 of last year. We founded the Synthetic Aggregate Association. We're a nonprofit organization founded in Atlanta, Georgia. And I'm one of three founders of the association. We're all passionate. And in general, we're focused on taking recycled materials and turning them into functional aggregates that can be used in concrete and building products. That's the overarching mission of the association. So a little bit background on myself, how I came to be involved with synthetic aggregates. So my entire career, I've been involved in the architectural, engineering, construction industry. And my first introduction to synthetic aggregates goes back 15 years. So we were involved with getting the expanded perlite material in use in water filtration systems. So this was pretty interesting. I never really was involved with synthetic aggregates. And so expanded perlite was used for water filtration. And the systems were regenerative media filtration systems. And the expanded perlite is the media to remove the dirt. Those regenerative media filtration systems to this day have saved literally billions of gallons of water. So in the aquatics industries, when you filter water, sand filters, you'd basically flush the water and just dump that water down the drain. Regenerative media filtration systems stay in a closed loop and don't waste that water. So that was expanded perlite. My next project was involved with the New York City Mass Transit Authority, where they were drilling tunnels from Queens to Manhattan, and I was involved with a project that developed polymer concrete. And polymer concrete, to meet the specification, we ended up using hollow glass microspheres. And hollow glass microspheres delivered a very strong product at a lower density. So it lowered the unit weight of the polymer concrete substantially, still met the specification requirements. So at that point, I was super intrigued, right? So now you can take an engineered aggregate, into a matrix and as a functional filler and really change kind of the performance of the product. So then I was completely hooked at that point. From there, I went on to work for the global leader of expanded glass. And so this is one of the most widely used synthetic aggregates on the market. It's called expanded glass. So I work for this company. They're a German-based company. They have plants in Germany, and they put a plant in Canada, so serving North America. So I ran U.S. and Mexico markets for them for 6 years, and I really, really love that material. I currently work for the U.S. leading manufacturer of foam glass aggregate. So this is, again, taking glass as just another type of foam glass. So there's expanded glass and there's foam glass aggregate. Foam glass aggregate is more of a gravel, more of a larger piece or a larger chunk. And the expanded glass particles are typically smaller. Expanded glass particles are usually, less than 4 millimeters in size. So that's my background in synthetic aggregates. And again, to this day, I work, daily in this market. So the Synthetic Aggregate Association in general, so I will just read a little bit about our mission statement. So our mission is to revolutionize the architectural, engineering, construction industry by being a catalyst for the use of innovative, sustainable, and high-performance synthetic aggregates. And when we do this, we're trying to meet or exceed the performance of traditional aggregates. So we're not just taking waste and losing it into concrete just for the sake of sequestering it or getting out of the way. We're focused on taking aggregates and making them high performance. And so this is a big function of ours. And the goal is to foster a circular economy that transforms materials that would otherwise end up in landfills and turn them into a valuable resource like synthetic aggregates. So this is the nature of a circular economy. And a lot of this is local, right? If you take your local, a good example is recycled concrete aggregate, right? You can take concrete from the demolition of a building, you can crush it up, and you can get it back into a proper particle size to go into concrete. This is a great use of, and that incidentally is a synthetic aggregate because it already had a use in the market, and then it's getting a second life, right? So and I'll get into types of synthetic aggregates and there are other different categories, but that's a great example where you're taking a material from the region, from the city, from the community, putting it directly back into a new construction project. So I think a lot of synthetic aggregates, the benefit is that they can be regional, they can be local, and this technology can be deployed in Dallas, in Denver, in San Francisco, all around. You can have it regionally. All these materials are typically available regionally, and then you can put them directly back into the construction process. So again, the vision we have is twofold. We want to promote the adoption of recycled materials in construction, and we want to foster the innovation in aggregate manufacturing, because at the end of the day, almost all of these products, not all of them, but most of them, are manufactured. We're talking about taking waste stream material and manufacturing it into a useful aggregate, and I think that's really a great thing. So what are the types of recycled materials used to make synthetic aggregates? There are some that are obvious and some that are not obvious. So I'll just go through a couple of them. Number one is glass, right? Glass is widely available and relatively easy to recycle and use. Plastics is the elephant in the room, right? We'll get into that a little bit more. Then there's industrial byproducts. Industrial byproducts is pretty extensive too. You're talking about blast furnace slags, fly ash from coal-fired plants, all of these things. And there's other ones. And then you have recycled construction debris, like I just said, recycled concrete aggregate, right? So these are kind of, there's other subcategories within these categories, but these are really the big ones. And I'll talk about glass initially. So glass, this is really the low-hanging fruit. Glass is inert, and glass means it's not biodegradable, it doesn't react very much, and it doesn't really degrade, right? This is a great one. This can be turned into multiple types of synthetic aggregates, and there are literally millions of tons available globally. One of the key things when recycling glass into synthetic aggregates is, and one of the things my current company focuses on, we take a grade of glass that's really doesn't have any commercial value. So when you're recycling glass, you're sorting it optically for color, right? Because different color means different chemistry. So the chunks are larger, it's optically sorted for color, and there are good commercial uses for this. But as the material gets finer and finer, no longer can be sorted optically for color. This material is largely waste material, right? We're landfilling 97% of this small particle glass to landfill in the United States currently. So this is what we take. We take this into our process, and we turn it into our company. My company that I work for turns it into foam glass aggregate, and other companies will turn it into expanding glass, and there are other products it can go into. So glass is right there, and glass is available pretty much in every region. The next one is plastics. Plastics are much harder to recycle and turn into a functional aggregate, right? And this is the most available feedstock or waste stream that's available. You're talking about 300 million tons available globally. And this is a problem, right? And so if we can take this material, turn it into a functional aggregate, again, regionally, you can take the recycled plastic from San Francisco, turn it into a functional aggregate and put it back into construction projects in San Francisco, right? This is the circular economy. So the challenges with plastic are many, right? So it's non-biodegradable. It's not biodegradable, and it's all types of plastics. So it's a mix. So separating plastics is expensive, very hard and very expensive. So we need advanced technologies to do this, right? So as the technologies get better, and a good example is pyrolysis. Pyrolysis can be used, right, to kind of change these materials into something different. So there's a lot of innovation with plastics. I want to cover a lot of topics here today, so I won't drill right down into that. But again, the Synthetic Aggregate Association is drilling down into that, right? And we are assisting with development of technologies, implementation of the use of these materials, and acceptance, right? Awareness and acceptance is a big thing. This is one of our big things. We want to focus on awareness and acceptance. And people aren't understanding that these materials are out there. I don't know how many people in the construction industry know that there's expanded glass and foam glass aggregate available in the market, and it is available in the market. In fact, expanded glass is in lightweight tile adhesives, right? It's in a lot of different materials. It's already there, right? So people just are unaware that it's there. So at the Synthetic Aggregate Association, right now, currently, we have 20 synthetic aggregates listed on our website that are commercially available. What we do, Seth, is we break those aggregates down into 3 categories. And this is where we're trying to be a little bit of an umbrella association where we incorporate a lot of different types of synthetic aggregates. So the 3 categories we break down into are non-reactive aggregates, reactive aggregates, and volume additives. And I'll explain a little bit about these. So non-reactive aggregates are, as I would just explain, foam glass aggregates, good one, expanded perlites, hybrid mineral polymers. These are all non-reactive. So these materials are going in, they're volume fillers, they're filling up they're functionally taking up space within the matrix, but they're not reacting, right? They're not serving as binders, they're not reacting. Reactive aggregates are fly ash, blast furnace slag, and other minerals that have been somehow modified to some extent. See, and the difference between a natural aggregate and a synthetic aggregate, natural aggregates come out of we mine them. These are natural resources, right? We're going in, we're ripping them out of the earth and mining them. The only thing that's done with a natural aggregate is size reduction and then particle size ranges, putting them in certain particle size ranges so then they can be used in concretes and other materials, right? So this is a natural aggregate. Nothing else is happening to a natural aggregate. It's just being mined, typically being sized down, and just being screened and sorted into different size ranges. A synthetic aggregate takes it a step further, right? You could start with a natural aggregate, although our focus is to start with recycled materials. But as an example, you can mine shale, and you can mine slate, and you can mine clay, and you can expand it, right? So in a heating process, this material is expanded, and it imparts different properties to the material. Usually, just makes it a little bit lightweight and put some air bubbles in it. So that is a synthetic aggregate because once you go one step beyond sizing it down and separating into particle sizes. If you do one more step, it becomes a synthetic aggregate, right? Now you are doing something to it to enhance the performance of the material. So that's in general what we're doing. So that's the key to the synthetic aggregate market is to identify these performance attributes that can be delivered into the synthetic aggregates. So at the association, we want to focus on our challenges and opportunities. I mean, the goal for us is to overcome challenges so we have more opportunities for adoption of these materials. So some of the challenges, Seth, we have are the lack of standardization and guidelines and specifications. I'll get into that a little bit more as it pertains to the ACI and ASTM. Then we have limited awareness. I mean, there's really limited awareness, and there also can be misconceptions about the performance and reliability of synthetic aggregates. And that's important. That's what the association is there to do. We're there to help manufacturers help develop these guidelines and specifications so it's standard, right? So if you have a plastic, an aggregate that's, say a hybrid mineral polymer, which is basically taking plastic, granulating it, getting into a form of an aggregate, And then some people put a mineral coating on it. Actually, some people can use CO2. You can actually sequester CO2 into a plastic aggregate. And this is super exciting. You can take CO2, pump it into a pressure vessel, and if you add specific minerals to it, those minerals can precipitate and form a calcium carbonate shell around the plastic. Now that really makes a great functional aggregate. So there's a lot of things, innovation here, where you can take these feedstock materials and work them, into a more functional aggregate. That's one of the things that we're going to try to do, Seth, is Saw will eventually have a rating system. And so we're going to rate the feedstock, and we're going to also rate the finished goods. And we're going to have a Saw rating, maybe 1 to 5. How good is it? For example, feedstock. If the feedstock is glass and it's coming directly from the waste stream, this is post-consumer recycled glass, it's going to have a high rating, right? Because this stuff is going to landfills. As far as finished goods go, say, precast panel. Now, for precast panel, so we have in the association, we start with feedstock people who have these recycled materials, and a lot of them don't know what to do with them. So this is another area where SAW connects the dots. So they have this material, whether it's a municipal recycling facility or whatever, they have the material, they don't really know where to go with it. So we're kind of going to be a resource for that. We can connect them with a manufacturer that's making a synthetic aggregate. So the synthetic aggregate itself, the feedstock, would have a rating. Then the finished goods. So then we also have manufacturers. We have ready mix companies, precast companies that want to know what's the latest and greatest thing, what's new, where's the new technology coming. So they could look at some of the synthetic aggregate producers and say, we'll have a rating. So if they want to get something that's almost zero carbon or whatever they're looking for, performance attributes and also environmental kind of ratings for these materials. So we're a resource where they can find those things. That also boils down into EPDs, global warming potential, and LCAs, life cycle analysis. We already have a little bit of internal support from the EPA to work on some of these things, so this is also a focus of ours. And I throw out an example. We have one of our reactive synthetic aggregate mineral members who has just received his EPD, and his number is 43 kgs per CO2 equivalent. That's a super low number, and this is a reactive mineral. So that material can replace Portland cement. So this is a place, SAW is a place where people can go and find a material like that. Say, we want to reduce our Portland cement content of our materials. You can come to us, come to our website, and look at our reactive minerals, the synthetic aggregates, and choose one. And these will have these EPDs and these environmental numbers on our website. We'll also help the companies achieve these numbers. These things are sometimes, cumbersome to come upon these numbers and get them sorted out. But that's some of the main things about the challenges that we have. There's also economic challenges, including the cost of production and scaling up manufacturing, right? So this is, as the technology gets out there, a lot of these things, have to be done at scale, right? In order to be profitable within the market, you kind of have to do these things at scale. You're not really going to produce a couple thousand tons of material and be profitable. You're talking about needing to produce hundreds of thousands of tons, millions of tons of these materials. So that's another potential there. But as far as the opportunities for this material go, it far outshadows the challenges. The growing demand for sustainable construction materials is absolutely massive. $1.26 trillion is estimated by 2033 to be going into specifically sustainable construction materials. And at the Synthetic Aggregate Association, we want to be a catalyst for bringing more of these materials to the market. So that's our focus. And to do that, we have to have advancement in material science, and we have to have advancement in recycling technologies. This is a big thing. So the feedstock, the quality of the feedstock. I've seen, for instance, expanded glass manufacturers that take in a very, very nice, clean glass cullet, right? Very low LOI, very low organic content. That material is great. You take that initially into your process, you're ready to go. Other manufacturers will have to take in whatever they can get, right? And this is the glass looks like it's dirty. There's straws and plastics and organics and ceramics in it. And then it's expensive. You have to clean it. Somebody has to clean it, right? You either receive it at your plant clean or you have to clean it yourself. So these technologies are great. We need a little bit of advancement in recycling technology, and I think that's coming. So And one of the things that SAW is trying to do, we have to, the role of the public and private sectors to foster innovation is key. So that's what we're here for. We're working. We have a lot of academics. In fact, I will plug our upcoming webinar at this point. So we're partnered with the University of Miami. Siva Ramathan is going to present on February 4th. Webinar for us and the topic is biochar. It's going to be a great webinar. So we have good buy-in from industry and academia alike, where everyone's kind of on board with what we're doing. And so some of the things that we're doing internally with the founding membership and the initial guys that are working on this, we're focused on the ACI and ASTM. And this is where we need acceptance. We need kind of better rules and better guidance on what, how to get these things into market, how to get accepted. Performance standards and environmental standards are really key. So, and the ACI, again, we were at the ACI convention in Philly. We'll be in Toronto in the spring. I personally sit on the ACI Committee 213, lightweight aggregate structural concrete, where I'm constantly lobbying for the inclusion of synthetic aggregates in these materials. We have one of our founders is sitting on ASTM committees. So we're in these committees and we're trying to see what we have to do to foster the acceptance and the inclusion of these materials. And again, a lot of this is focused on sustainability. I'm a lead AP. I recently just got my ENVSP, which is the Envision program, which is through the Institute of Sustainable Infrastructure. So it's basically lead for infrastructure. Super cool thing. And I want to talk about this one topic here. So it's just an example of how SAW can move the ball forward. So if you're talking about LEED, the LEED program, when it looks at recycled materials, it looks at recycled materials and the material resource credit, and it gives points for the use of recycled content. But the way they quantify the use of recycled materials is they do it by weight. And, they don't know what they don't know, right? So I'm actually lobbying right now, the United States Green Building Council and LEED, because they're going into version 5. It's going to be out for registration at the beginning of this year. And my point is, when you're talking about materials that are lightweight, it does a disservice to take into the calculus by weight, right? So materials are lightweight. Sand, ranges from 100 to 112 pounds a cubic foot. Lightweight sand and ultra lightweight sand is about 20 to 30 pounds a cubic foot. So if you take it into the calculus by weight, you're not capturing what the essence of what you're trying to do. So my point to them is I would like them to have a cutoff at 45 pounds a cubic foot. So every product or material that's less than 45 pounds a cubic foot should be considered lightweight, and it should go into the calculus by volume, not by weight, because the 10 pounds of lightweight material is volumetrically could be 3 times the volume of material that's by weight. So this is a great example of, we know this because we're working with these materials every day. And so, again, I feel like it's going to be well accepted. I've had initial conversations with the USGBC, and this is the kind of thing that SAW is going to lobby for. And we're going to get in there, we're going to lobby for that. And that helps our manufacturers. It helps the people who are making these synthetic aggregates. They just generally get more lead points, all right? Because a lot of synthetic aggregates are lightweight, right? You're in a heating process or whatever process you're doing, you're lowering the unit weight or the density of these materials. So that's just a great example of, what we'll do, how we can affect, some of the standards that are out there. So the other thing we need to do when we're talking about these materials is to minimize waste streams. I mean, waste streams are everywhere. If we can minimize waste streams by reintegrating recycled materials into the construction life cycle, that's going to lower greenhouse gases, and more importantly, it's going to lower landfill volumes. And again, this is regional. If you take these materials that are regionally going into a landfill, you save them from the landfill, you innovate, and you have better aggregate manufacturing technology available, and you turn these into functional aggregates that can be used regionally. So now that material goes into the foundation of a new school rather than into the landfill. I mean, this just seems like common sense to me. And this is something what we're really going for. So this is really reducing the construction industry's reliance on natural aggregates. This is conserving a natural resource. Again, where does sand and aggregate come from? We literally dig it out of the ground, right? I mean, you're not going to be able to dig it out of the ground forever. I mean, it is a finite resource, and it just makes sense if you can take existing waste streams and turn them into these materials. And again, we're not focused on doing this just to be green or just to be sustainable. Our core mission is to make sure that these synthetic aggregates meet or exceed the performance of traditional aggregates. And it's been proven that it can, absolutely. Expanded glass and foam glass have been used in Europe since the 80s, right? We are definitely behind the curve here in the United States. I was shocked when I first started working for the German company in 2014 and how well accepted, widely accepted it is in Europe. And I had never even heard about it. I mean, I'd been in this industry my entire career. I'm not going to tell you how long that's been, Seth, but I can say that Jerry Garcia was playing live with the Grateful Dead when I started. So that's, it's been a while. So, and I'd never seen these materials, but in Europe, it's just widely accepted in a great material. So now what are the impacts on the industry? I think the adoption of synthetic aggregates in general, when you're looking at the AEC industry, adoption of synthetic aggregates is going to bring the construction industry in line with global sustainability goals like carbon neutrality, waste reduction through reuse. So we can adopt these technologies, raise awareness, raise acceptance, get these materials into the construction industry. And again, that aligns the entire construction industry with everybody's goals. Everyone wants to be more carbon neutral. Everyone wants to reduce waste and reuse materials. And what we're saying at the Synthetic Aggregate Association is it's possible. It's very possible. And everyone just needs to get behind it and work towards these goals. I don't know if you want to talk. I feel like I'm just going on and on my talking points. Do you have any questions on specifics that I can answer for you? I'm really a technical guy. I focus on application and use in these materials and applications. So if you have any specifics, please jump right in.
So you went over the things that are preventing this to be widely adopted. Which one is the biggest challenge right now?
So the biggest challenge is not having specific standards in place, right? So we need standards for use, and we need standards for testing, right? So to qualify, when you're looking at a natural aggregate, a good example is, let me go through some of the uses where can you use these synthetic aggregates. Wet cast concrete, which is ready mix, precast, wet cast concrete in general. No problem. Whenever you have a sand and aggregate in these mixes, so let's look at a yard of concrete, for instance. So in a yard of concrete, you have on average 17 to 19 cubic feet of natural sand and aggregate. You can go ahead, and I've been involved with this for a number of years. You can go and you can back out, say, 8 to 10 cubic feet of that natural aggregate, replace it with a synthetic aggregate that has a lower density, and then that concrete can meet ASTM requirements for lightweight concrete, which is 115 pounds a cubic foot. So simply by just taking these materials out and replacing them with a lightweight synthetic aggregate, whether it's foam glass or whether it's mineral polymers, whatever it is, you can come in and you can lower the unit weight just by replacing these materials. And typically, Seth, you just do it by volume. You come in and you take out a portion of these materials, but we have to make sure that the aggregates we're using meet the grading tables, right? So a lot of the companies are developing the synthetic aggregates to match the grading table. So you have the proper particle size distribution. As long as the proper particle size distribution is there that matches existing grading tables, then you can just simply back out the natural aggregate by volume and replace it with a synthetic aggregate. So that's kind of the low-hanging fruit there. And this also then goes into dry cast concrete, right? CMU block manufacturing, right? Block manufacturing is largely, that's like 90% aggregate, only 10% binder, right? So it's a great product. Again, you can bring these synthetic aggregates in. Synthetic aggregates, at the top of the heap are what they're doing: density reduction, improving thermal performance, and increasing acoustic absorption. These are kind of the low-hanging fruit things for synthetic aggregates. So you want, in a lot of cases, you want that for just about all concrete products. Then you get into dry mortar products, ready-to-use bag mixes, tile adhesives, stuccos, engineered mortars. All of these materials, guess what's the backbone of all these materials? Sand, basically, right? So again, you can just take out a portion of the natural and put in a portion of the synthetic aggregate. And in fact, a lot of these things, you're not doing it just to get rid of, waste or just put it in to be green. I mean, you can increase strength, you can increase durability, you can increase flexibility. I can use the example of expanded glass. When you put expanded glass in a stucco, you lower the E modulus of the material. You put expanded glass into veneer stone, for instance. Veneer stone, very brittle. It's always cracking, right? And if you use some of these synthetic aggregates, you can adjust the E modulus. You can make these materials less brittle. Again, back to my original, way back in the day, one of my first projects using hollow glass microspheres and polymer concrete. This was incredible. We put that in for performance. We were putting it in to lower the unit weight. So again, these things can be very, very functional. And then the uses go well beyond what I just described there. So you have fireproof panels, you have fire suppression media. Both of these things can be achieved specifically with synthetic aggregates. Thermal insulation boards can be made exclusively from synthetic aggregates. Water and air filtration is another one. I started out explaining the regenerative media filters using expanded perlite. That's a great opportunity. Then you can get into other industries like fiberglass and sheet molding compounds already use hollow glass microspheres. So the synthetic aggregates are being used, largely, but a lot of like hollow glass microsphere doesn't necessarily utilize waste stream material. That's going to start with borosilicate glass. So, it's a synthetic aggregate, but probably not historically with, recycled materials, but that could change, right? We can incorporate these materials in. Mineral casting is another good one. Mineral casting typically uses calcium carbonate. Again, synthetics can be used. Soil additives. So great example, comparison of is perlite. A lot of times I'll use perlite in soil additives as a hydration extender to entrain air. Well, you could use a synthetic aggregate and it performs much better. Still, you're going to entrain air in that soil matrix. Still, you're going to absorb and retain water, but it's a synthetic aggregate. And the synthetic aggregate is stronger. So the perlite material is going to break down, right? It's not very strong, so it's going to break down. The synthetics can be engineered to be stronger. So they could go through a couple more cycles, right, in that soil where the perlite's going to break down and you maybe get 1-2 cycles. With the synthetics, you're going to get maybe 3 or 4 cycles because it's more robust. It's not breaking down as easily. Yeah. In the same way, and we're talking about there's water retention, right? And this is kind of one that everyone kind of knows about, is using synthetic aggregates as internal curing of concrete, right? This is a big thing. I think you had a gentleman on one of your last episodes that was talking about biocarbon, using biocarbon as an internal cure. And the reason that works is because that's holding on to the water, right? It's absorbing more than its weight in water. It's hanging on to it. Then it's slowly, begrudgingly giving it back to the matrix to catalyze the cement. This is internal curing. So there are so many opportunities for the use of the materials. It's I don't want to say it's limitless, but it's pretty close. But you have to be accepted. It has to be understood. It has to be accepted, and this is our focus.
So, which you said just lightweight aggregate and structural concrete is the ACI. Is that right? That you're trying to get?
Right. Well, that's the committee that I sit on the lightweight committee for lightweight aggregates. And
what's the pushback from that group as far as how they view synthetic aggregates?
So there's not so much pushback from that group. It's having a good understanding and having acceptance. So in that world, if you want to put synthetic aggregates into structural concrete, you need ASTM 330. So ASTM 330 is the governing standard for the use of lightweight aggregates in structural concrete. So this is a great standard, and synthetic aggregate. And here's a case, Seth, where we don't really need a whole bunch of policy or specification changes because it works. For instance, the company I work for that manufactures foam glass aggregate, we have 330 approval. So our material went through a rigorous, the 330 is a litany of tests, chemical characteristics, everything all the way down, shrinkage. There's a whole bunch of tests that collectively form 330, and our foam glass aggregate is 330 approved. So in that case, lightweight concrete, it's that's the one you go to. If you're going for dry cast concrete, then you're going to go for ASTM 331, and again, this is the governing standard for lightweight aggregates in dry cast or CMU or masonry units. So some of the standards are there. They just, in general, let me go back to where I said we have 3 categories for our aggregates, for the synthetic aggregates. We have the non-reactive, we have reactive, and then we have volume additives. The reason we have volume additives is historically the definition for an aggregate, and we're the Synthetic Aggregate Association. Again, this is an older term, and we want to expand on this term. So aggregates typically mean that it contributes to the bulk, the structure, or the overall volume of the matrix, right? So they're basically saying, it has to make up a certain percentage volumetrically of the matrix to be considered an aggregate. What we're saying is today's technology, there's nanotechnology, I'm going to use two examples of why we added the category of volume additives. So volume additives, we have one company that takes waste foam. I don't want to tell you what kind of foam because it's proprietary, but they take foam from the construction project. They take the foam and they turn this foam into an additive for concrete. It's an aqueous material in the end, but that material goes into that concrete and it volumetrically takes up some space in the formulation. And so that's really a volume additive. The other cool one, and really this is kind of a startup company, and this is why we're here, right? To help companies like this. There's a company that takes polypropylene twine that's used to wrap hay bales, right? So in the agriculture industry, they get hay bales and they're wrapping these bales with polypropylene twine. You wouldn't believe the tons of polypropylene twine waste that comes out of this agricultural industry. So this company recognized the presence of this material, the need to do something with it other than landfill it. And so they take this polypropylene twine, they bring it into their process, and they turn it into a functional fiber that can go into concrete. And this is something where it's going in, but it's going in at a smaller volume. So we feel like companies like that, because of the recycled content value, just simply saving it from the waste stream, saving it from landfill, and turning it into something that can be functional. It's functional. We don't call it a volume additive because it's volumetrically taking up space. We wouldn't say it's a performance additive. There's already specifications and groups for performance additives. This is it's going in. I don't want to say it's inert because it's really not inert, but it's in there just taking up space, and it helps with some reinforcement and it helps with a few things. But mainly, it could be used in lieu of other things, and so that's those two materials. These are both materials that are if they otherwise weren't used and kind of had some, they're synthetic because they're taking it from the waste stream and they're enhancing it. They're sizing it and then they're enhancing it and they're manufacturing it to go into these products. And that's really, really incredible. And so that's why we have that category of volume additives. And we're really excited about that. This is at the core of what we're trying to do something like that. Rather than landfilling all that material, you can take that material directly into concrete. So both of those are good examples.
Have you all taken the approach that I don't know if synthetic aggregates can't or have this issue, but I know our standard aggregates do, is the alkali silica reaction, ASR.
Yep.
Is you taking the approach saying your synthetic aggregate reduces this, or you mentioned durability, so I was just curious.
No, so we test for it. So we'll test for ASR and make sure that it's not that reactive. A lot of the synthetic aggregates, for instance, foam glass aggregate, it does not contribute to ASR. It just comes in just under the standard of 1260. And the way it does it, because that's silica that's present in foam glass. I'm just going to use foam glass as an example. The amount of foam glass largely has a unit weight of around 20 or 25 pounds a cubic foot. So it's largely air, right? So if you look at one of the grains or one of the particles, the area inside the particle is 65 or 75% air. So just simply, there's not enough silica present in that. So if it were a solid, this is why you don't just crush up glass and put it into concrete, because you will have an alkali silica reaction. But the unit weight of crushed up glass, call it, is literally 5 or 6 times heavier than the foam glass. So the foam glass just doesn't simply have enough silica present to affect the matrix. So that's just a good example of, everyone, especially with glass, people think, well, my ASR, and it's true. So glass cullet will have adverse ASR effect on the concrete. But when you have aerated silicon dioxide, not so much. So it's important, and it's important for us as a group. So we have collectively we have a lot of very knowledgeable, smart people that have been around this industry for a long time. So we can help companies, figure out, is there an ASR issue? But absolutely, it has to be addressed at all stages. How does it meet the standards, right? I think plastics has some of the biggest challenges because there's no, glass inherently goes back to, it's silicon dioxide, right? It starts as sand, becomes glass, and the chemistry largely doesn't change. Plastics is a bigger challenge, but this is where we need advancement in the technologies, and I think it's coming, and plastics is where you have 300 million tons of non-biodegradable plastic available for use. So this is where we need some additional standards and some innovation.
Yeah. Yeah. Well, what pops in my head with plastic is it should be used as fuel to make concrete or cement. Is a good use for it, because I think people have in their minds when you burn plastic that a bunch of pollution goes up in the air, and I think educating yourself on what plastic is really made of and what happens when you burn it,
Right.
It would change people's perspective of that.
Well, the challenge with plastics also is that you have 7 different resin types available, currently, and these are all different chemistries, right? So it's super hard to, I think plastics, to be able to economically sort the plastics, because if you had those 7 resins, plastics in the 7 different categories and you separated, without contamination within the 7 categories, you could make all kinds of things. You could be very effective in utilizing that material, but to get to that point is cost prohibitive right now. So this is where the innovation is required. Innovation in recycling technologies, innovation and recover and recycling technologies, and then innovation in the aggregate manufacturing itself. I think this is, and how do you get there, Seth? Is just by having conversations like we're having, just awareness and acceptance of these materials, and understanding that, I think when you come to it by saying, no, we're going to make a synthetic aggregate that meets or exceeds the performance of traditional aggregates, rather than saying, we're going to figure out how to put plastic in concrete. Well, these are 2 different statements, right?
Yeah.
These are 2 completely different statements, right? So this is the focus here. We're very serious about it, and largely there's the technology, at least, for some of these waste materials, the technology is existing. It's already there. Again, more widely adopted in Europe. And incidentally, how can they do this in Europe a little bit more effectively than we can? Because of the way they recycle. The percentage of materials that are recycled compared to us, these probably aren't 100% accurate. I'm going to paraphrase, but it's something like 20% in the United States, 80% in Europe. This is very close to what it's at. So we recycle 20%, they recycle 80%. And when they recycle 80%, they don't do it in a caveman method. They recycle, and it's all separated. So when industry wants to take these materials, it's much easier for the industry to take materials. There's more of them, and they're better sorted, right? And you don't have to, because if it's not sorted, if it's not cleaned, if it's, then the onus goes on the manufacturer. And this is back where I was talking about the economic challenges of in production costs. If you have to sort it, if you have to clean it, that the cost of that goes ultimately to the price point of the finished product, right? So as we get better at that, we'll get better at using these materials. Again, once the material, I'd say on average synthetic aggregates cost 10 or 15% more than standard aggregates today. That's a pretty good average. That's not too far off, but we could do better. And this is how we have to do better, by better sorting, right, and cleaning, and just better recycling techniques.
Yeah, that's a perfect place to stop today, I think, Travis.
Awesome. How
do you want people to reach out to you if they want to learn more?
Just simply go to the Synthetic Aggregate Association.org. I'd go to there, and please also join us on LinkedIn, Synthetic Aggregate Association. We're present on LinkedIn, but just to our website, syntheticaggregateassociation.org. We're gonna be offering foundational memberships through the end of this quarter. We're going to be voting our board into place in February, so our board will be in place by March 1st, and we're offering these foundational memberships. So anyone who joins the association by the end of Q1 will be considered a foundational member. As the association grows, there's only going to be so many foundational members, right? We expect to be a very viable and formidable association going forward for years and decades to come. So whoever joins before the end of this quarter will be a foundational member. Foundational members get instead of getting a year, they get a year and a half. So we're adding 6 months on for free. and then that foundational membership status is going to be yours in perpetuity. So we're kind of using this as, you know, an incentive to get people to come and join the group.
Cool. Sounds cool.
Awesome.
Well, I appreciate you coming on the show and sharing today about synthetic aggregates. We'll have to get you back on, and we can kind of dive into those specific aggregates on future episodes. Sound good?
Seth, thank you for your time. It sounds great. I really appreciate your time and having me on, and I look forward to talking to you again.
All right. And folks, until next time, let's keep it concrete.